for the invitation. So my motivation is so somehow in this program, so to classify final varieties, usually mirror symmetry. And so as we saw in team stock, it is expected mirror symmetry statement. Then on one side we have final varieties. Let me just put with mild polarities. And on the other side, we have Laurent polynomials. With nice properties. And so basically this mild, I will talk about, so when this mild singularity will be terminal, and this nice property will be rigid. So, and I will state the statement in all dimensions, although the proofs, so the theorems that I will mention work only in 3 dimensions. And we can, as was already mentioned, so we can look this side up to Gorenstein deformations, and these are up to mutations. So this is the mirror symmetry statement, and there's been a lot of work how to, from a Laurent polynomial, construct a Fano variety. So let me just mention. So I think the first program that actually took a Laurent polynomial and constructed Fano was so-called Laurent inversion. So by codes, Asperger, and for instance. And then, so lately, there were like 2 programs that really produced some results. So, Tim already mentioned. So there is a work of so Tim Bertnitz and Helge Ruddat and Alessio Corti. So basically using log geometry. Also, of course, based on the Gross-Ebert program, and also based on smoothing toroidal crossings. That this is a paper that we did with Simon and Helge. And so what I will talk today is just so how to construct from a Laurent polynomial some smoothing. So hopefully in higher dimensions Fano is just via toric deformation. So toric deformation. So this we will talk today, and I will present the latest results that are already on our high. I will also talk about generalization in higher dimensions, what can be done, and so on. Yeah, okay, and so I have the same problem as Javier had. So basically, I need to apologize to all the people that were here last year, because the talk will be very similar, though I stated last year conjectures that are now here. So, actually, some of them. So. Okay, so my setting will be so P is a lattice polytope, and so okay, this will lie in lattice N, and so I build a cone sigma cone over P, and this will lie in N tilde, which is just N. So we put it on height 1. So we put on height 1, and we build a cone over this. So we have a our So our variety that we are actually studying will be this guy. So this is affine Gorenstein variety. And since most of you are interested in projective settings, so let me just mention that if you study the formation theory of affine toric varieties, by comparison theorem of Kleber, you also get immediately the formation theory of one dimension lower, so one dimension less of the corresponding projective variety. So you can build an affine cone and study the formations of an affine varieties, and then you get the so the projective deformation. So by this comparison theorem, you build affine cone actually lies completely inside the deformation theory of affine cone. So you can actually see the universal base space of the projective guy inside. You just take the degree 0 and then you see it there. So basically, if you understand the deformation theory of affine guys in all dimensions, then you also understand the corresponding deformation theory of projective varieties. Projective. So far, I'm just doing Gorenstein, so I'm not doing Gorenstein, but I believe that if you replace deformation by Gorenstein deformation, the statement should be very similar also. But okay, we will focus on Gorenstein for this talk, and also all the examples and the theorems will be stated for polygons.
So Gorenstein would be to put it in height.
Exactly. You put it in and so basically via this program you can only get panels that are very empty. And if you do the Gorenstein, then you get them. Okay. So now what is known about toric deformation theory? So in the late 80s, there is a Collard Shepard-Barron paper. So they do the universal. They describe universal deformation space for two-dimensional affine toric singularities. So these are cyclic quotients. Singularities. And then so they also show that there is a very nice relations. So deformation components are one-to-one with something that they call P resolution. And this is already so late 80s. And then mid 90s, Klaus Altmann have a result for, so he described universal deformation for isolated Gorenstein. Singularities. And again, he had a very nice description of what the components are. So the deformation components are in one-to-one with maximal Minkowski decompositions of polytope. So what means isolated here? So let me just say, so remark, if P is a polygon, so two-dimensional polytope, then XP is isolated if P has all edges of lattice length 1. So so for example, what Klaus show is that if we take, let's say, this is a classic example of hexagon, all lattices needs to have lattice length 1. So there is no other vertex here. So there is no other lattice points in the middle. And so if you take Minkowski decomposition, you can do it like this. Yeah. So this is the you just do the as a set, like this is called Minkowski decomposition, and you get this plus this is this guy, and you can also take this plus this plus this, and again you get and so basically isolated Gorenstein toric variety that corresponds to this polytope. So you build a cone over this, and you have an isolated Gorenstein toric variety, has two components, namely corresponding to this Minkowski decomposition and this Minkowski. And you can even see the dimensions. So this is kind of two-dimensional, this is three-dimensional. So okay, so this is what's known in and so then later there were some generalization of this result, and but the main thing why this works is because the tangent space, so T1 is concentrated in one lattice degree, namely the Gorenstein lattice degree. So this is 0, 0, so 0, 1. So the degree that all the ray generators have a value 1. And in general, the tangent space of deformations is spread over many lattice degrees. So the main problem in toric deformation theory is how to handle different lattice degrees. And
it's done by my Budur too. This argument about, I thought Minkowski's
so this was later then. Yeah.
It was later.
Yeah. This was 10 years.
Yeah, Alphen was earlier.
Yeah, so this was like 95, and Budur was 2005, something like that. But yeah, so of course there are many generalizations, but not in a sense like this, that you really say what deformation components are. Yeah, there is not. But there are really many papers also. I was including some of them that you generalize to either you go into different degrees, not this setting, or what Budur did. So, yeah, there are many, and also Nathan Newton did some generalizations, but so far nothing was done with to say if you take more, let's say, I will focus today on non-isolated singularities, Gorenstein. So what are the components? That will be the main question. Okay. Okay, so this toric deformation theory started by idea of Alessio Corti, and so he basically introduced to me and Andrea Petracci an idea of how we might build from a Laurent polynomial so deformation of an affine toric variety. And so to state what we actually mean, let me just first talk about the tangent space in one example that already Tim introduced, but I will so far no Laurent polynomials yet, just this polytope that we already consider in few talks. So basically, how the tangent space look like? So tangent space will be so it's a direct decomposition of they come in so it's a graded you can always do grading. So torus gives you a grading, and then you just need to ask like in which degrees, lattice degrees, this T1 is non-trivial. So we already see that in this isolated case there is only one degree that is non-trivial. If we don't have isolated ones, so if you have edges that have a length that are so that have also they don't have lattice length 1, then basically those are, I will just say, not say precisely, but it has to be, for example, if we take M to be M will give you an affine function on this polytope. So if we take, let's say, 2, 1, 0, if we take this this R, let's put M because I will always use M. So if M is 2, 1, 0, this is okay because we can fit edge of lattice length 2 here, edge of lattice length 1 here, and here there is nothing to fit. And then also like if we have here 3, here 1, here -1 is again okay because we can fit lattice length 3, 1, and then if it's negative, there is nothing to do. So this kind of M's give you one-dimensional tangent space, and then the same with vertical ones. So we can take 2 here, 1 here, 0 here, -1 here. Again, we can fit edge of lattice length 2 here, edge of lattice length 1 here, nothing there. And so all these degrees give you one-dimensional tangent space, and you easily see that the tangent space is infinite dimensional. So because you can always do 2, 0, -2, -4, 2, -1, -4, and so on. So there is infinite dimensional tangent space. So an example which degree is not in the tangent space. So is if we take let's say 3, 2, 1. This is not because like this one. So there is no lattice length 1 here. So this is not in the tangent space, but all other degrees lie in the tangent space. And then the idea of
tangent space would be the tangent space for the big guy that you're going to deform your.
Yes. So the tangent space of the corresponding Gorenstein toric. So you put it on the height 1, and so this M in M tilde gives you an affine function when this is on height 1, and I'm telling you which are the non-zero degrees, and there are infinitely many. And now the idea of Alessio was that Laurent polynomials tells you which of these. So okay, what was known is that also by Klaus Altmann and then also by Magliuto. So if you take 1 degree, you can build one parameter deformation. So I think there was a question at some point when this triangle appeared: is there Minkowski decompositions here or no? In fact, it is, because what I mean, like in each of this degree, you can say that this lattice length 1 edge is a Minkowski summand of the crosscut. So that's how you build one parameter deformations if you know this theory of Altmann. Otherwise, just take it for granted. And then the main idea was how to connect. I mean, okay, this is this one parameter deformations that we know. And now the question is like, what is the whole deformation space? So which one parameter deformations actually combine to build like multi-parameter deformations? And the idea is that the idea of Alessio was that actually Laurent polynomial tells you which those which those one parameter deformations can be combined to build like to have multi-parameter deformations. So that's basically the setting, and I will now go into mutations. Any questions? Now mutations and the Laurent polynomial. So
infinite dimensional.
Yeah. Like you can always pick like 2, 0, -2, -4, and then you continue 2, -1, what is it, -4, -7.
But does it form like some sort of convex set?
It's always, I mean, as long as you have something that is non-trivial, it will be non-trivial also in T1. So these two will give you a non-trivial T1. Although, like, the equations will be only finitely many.
No, I'm saying the set of this exponents, whatever we call it, like this M's.
Yeah. These M's, yeah.
The form like a convex set, or like what?
So they are. So it's if you picture it geometrically, yeah. Some of them will lie on the boundary of the cone, and some of them will lie outside the cone. You see, like so for example, 2, 1, 0, this lies in the dual cone because it's positive on the. But then this guy doesn't lie in the cone. So
but altogether, what's the structure on them? Like
I mean,
There are some lattice points, right?
Yes.
So it's in somewhere, in some lattice.
yes. And
So
that,
what's the?
there is no like good structure. It's just as I said, like some of them lie on the boundary, some of them lie outside. But I mean, the easiest way to picture is precisely what I described here. There is no, I mean, like from the, I mean, I can draw like this three-dimensional picture in the dual cone, but there is not, I mean, like you just see what I said, like some of them lie on the boundary, some of them lie outside, but there is no like interesting structure. The easiest way to see is precisely with this lattice length that if you can fit. And this corresponds to the already known theory that if you do a crosscut, that there is a Minkowski summand of lattice length one inside, and that's why you know that there is one.
You said that T1 minus M always either 0 or 1 dimensional?
Yes. So okay, if it's not a Gorenstein degree, then yes, in 2 dimensions. So in the Gorenstein degree, the formula is that it's so in the Gorenstein degree is the number of edges minus 3, and then if you have 2 times or like k times r, you take the number of edges of lattice length k minus 2. So the formula for T1.
So there's one created piece per dimension.
Yeah.
Yeah.
But isn't there also some exclusion? You can say there's definitely some regions where it will not show up.
Yes, like if you cannot fit, so like 3, 2, 1. Like if you cannot fit the lattice, I mean, so like you can picture this in 2 ways. It's like I described, just you pick like you have an you have an affine function, and then you pick a lattice length 1 a line segment of lattice length 1 that is constant on this function. And if you can fit it inside, so like 3, 2, you already see that it cannot be fitted. But like 2, 1, 0, you see like 2 is fitted, 1 is fitted, 0 is fitted. So if it fits, then it's a non-zero T1. I think that's the easiest way to picture. In other words,
it's kind of not so far from the code. It's kind of next to it, but
if you want the other, like what people did in the past, so you can build a crosscut m equal 1, you intersected with sigma dual, and then you see that there is a Minkowski summand of this lattice length 1 inside, which is precisely this. And this so that's the two interpretations. Okay, so now mutations and Laurent polynomials, and so let me give you a precise definition what a mutation is, because there were many questions. So and I will give you so like for that you can picture in any dimension. So f is mg mutable, and here m is an affine function. And again, like I picture m as m tilde because it gives you an affine function on P, and g is a Laurent polynomial.
I was thinking by F.
F is in C and M is in M tilde. G is also in C. Laurent polynomial, so lying inside hyperplane where M is zero. So F is mg mutable if if F can be written as a sum of Fi's such that Fi divided by Gi, such that Fi is so lies in hyperplane M equals I, and Fi divided by Gi is a Laurent polynomial. So you basically you can divide Fi. This is G to the power. This is the index. Is a Laurent polynomial. And So then we just say that mutation mg is just sum of those fi gi. And let me do an example. So now if we actually have Laurent polynomial, 1, 3, 3, 1, 2, 1, and then we already know that either it's 2 or it's 3. So let me put 2. Those are the two interesting cases, yeah. So if we build one mutation, we can pick m to be 3, 1, minus 1, and then and g to be just 1 plus x. So if we take this g and this m, then mutation mgf is the following polytope. So you divide. So this is 1 plus 3x plus 3x squared plus x3, x to the cube. And you see, if you divide by 1 plus x cube, because this is 3, you just get a 1. So you have 1 here. And this one the same. So you have 2 times y, 2 times xy. You divide it by 1 plus x, you only get 2y. And the same, I mean, here when you have minus, you just add and you have 1 and 1. So this is a mutation.
Is this mutation in for some quiver or?
This is no. This is I mean, there is yeah. It would be. I mean, that was a part of Helge's talk. So it would be very interesting to build a quiver from a Laurent polynomial. But I think any work that was done, the mutations of a quiver doesn't really reflects the mutations of a Laurent polynomial. But I think like maybe there is. I mean, if you shift the definition of a mutation of a quiver, this might be.
And for polygons, we believe we have a correspondence.
But there is no. I mean, it doesn't.
9
Really,
dimensions is the difference.
I mean, but, so far it's really like. I mean, whatever. I mean, if you construct it via these wall functions of Gauss-Seibert any Laurent polynomial, it seems that it doesn't fit. The two notions of mutations doesn't fit, which is a bit unfortunate. Yeah, but it's actually something that I started looking when I hear Helge stuff.
How about categorically? Is there a connection? Can you put this? You know, there is I've thought about it. Mutation, categorical mutation, a defined notion. For polygons, the same. It might be true. Because this G to the I looks like exactly R arm and I would be gone.
Yeah. So yeah, I was also discussing some with him, and that would be very cool. Yeah, if you can add that. But I think it's so far it's a little bit it doesn't fit really.
I talked about this kind of work. Yeah, that's right.
Okay, so now just to continue this picture, this idea of okay, maybe I can even state the conjecture that we have with Alessio, myself, and Andrea Petracci. So there is a one-to-one correspondence between smoothing deformation components of XP and on one side, and on the other side you have zero mutable. I will say what this is: zero mutable Laurent polynomials on the other side. So with Newton polytope equal to P. So just to okay, so first, what is zero mutable was already described by Tim is just that you can mutate Laurent polynomial to 0. So for example, here we mutate it to this guy, and then we see that if we take 2, 0 here, you can mutate it to an edge, and then you can mutate it to a point. So if you can mutate it to a point, you say it's 0 mutable. That's a definition of being 0 mutable. So if we look on this example, what Laurent polynomials tells you that, for example, you pick these Laurent polynomials, and the idea was that those one parameter deformations, which can be gathered together to build a deformation space, actually tells you Laurent polynomial. So you see, if we have this Laurent polynomial, we lose the T1 degree that is 2, 1, 0, because this guy is not mutable by this affine function 2, 1, 0, because this is not divided by 1 plus y. So this is not there. So we see, like, if we look at the maybe I can give a definition, like so f is m mutable if it is mg mutable with where the Newton polytope of G is a line segment of lattice length 1. I always assume that all Laurent polynomials are normalized, so it means that the vertices have values 1. So then if it's a line segment, it's already like you have 1 on both vertices. Fine, yeah. So you see, like, the idea of these Laurent polynomials is that basically Laurent polynomials will tell you which of those degrees can be combined. And you see, we lose this 2, 1, 0 because this Laurent polynomial is not 2, 1, 0 mutable. And at the end, we will see that in fact there are 2 smoothing components of this guy. One corresponds to a Laurent polynomial that has a value 2 here, and the other one that has value 3. I hope.
But this is not an easy problem to figure out what are the m mutable, what are the m's for the m mutable. Like, maybe for polygons it's okay, but in general I think it's very difficult. Like it's like this linear property, like you have to test all possible.
Yes, it's so in fact, even for polygons, it's extremely hard to classify 0 mutables. This is something that we were thinking about, and it's I can give you an example, like even 157 triangle. That's some really so we don't have we have the descending division, and we have many properties, but we still don't have something that you can just put in computer and say, and it will give you like these are all the 0 mutable sets. So far, what we are doing, if you have like for example on the reflexive facets, they are classified, but they are using this statement that it's 0 mutable if and only if it's rigid. I will talk about it. So, and then with rigidness, you can you basically have all the computer can give you some Laurent polynomials even more than ones does not exist, and then computer checks. It can check like whether they actually exist, and you delete the few of them that are not. So far that's. But yeah, in general, yeah, of course, it's hard.
Close.
Sorry.
Computation grows.
Yeah. So yeah, it's a hard problem. Even for triangles, it's super annoying. I actually wanted to give this problem to my students, and then I realized it's way too hard to do. Yeah. Okay. So now some theorems. And so the first main observation that I managed to do is the following proposition. So if f is m mutable, and this holds in any dimension, it's just that you replace m by mg and it holds. If m is m mutable, then there exists one parameter deformation, and here explicitly constructed using equational flatness criterion. And here based on work by Klaus Altmann, myself, and Alex Constantinescu. So we basically we describe relations among equations in a very nice way. That was the first. I will not. I mean, it's still not nice enough to mention it here in this talk. But I mean, in fact, we managed to simplify Klaus Altmann settings from the 90s just by really describing those relations in a very nice way. So, so for example, this Klaus paper in 90s, if he would use those, the paper would be way shorter. So if he would just use those relations, so, and based on those relations, so this equational flatness criterion, we just leave the relations. I managed to actually explicitly construct one parameter deformation. So that the one parameter deformation exists was already known by Klaus, but to do it explicitly, this is the first main step, and then.
And this deformation depends on F and.
Yeah. So okay. Yeah. Sorry, I didn't tell you. So one parameter deformation of X over and so C, and I will denote this parameter by dm of this affine toric variety over dm, and this is the deformation.
And does the deformation depend on F or only on delta F?
It depends only on. So it always depends only on the Newton polytope. So even in higher, I mean, the statement is already done in higher dimensions.
Depend on F itself.
No, but no.
But it does depend on F.
You can, yes. So basically, you can. I mean, this is an. I mean, so you can state this for here. In other words, you can just look at the mutations of actually polytopes or and not mutations of Laurent polynomial. So this is basically a statement of mutation of polytope, but in fact, it's way easier to define mutation of Laurent polynomial and just say that then mutations of polytopes, you just take Newton polytope of F.
And this is deformation smoothing.
No, this is just one parameter deformation. Nothing that. It is the Codero-Spencer map is one dimension, so it's not trivial. That's all. And now the main theorem that I have is that so F now any Laurent polynomial, no restrictions. Then X so the affine and this is okay. So here this theorem is only for 3 dimensions. And then I will talk about possible generalization. So then this guy is unobstructed. In let me denote this by MF, and so those are degrees M such that F is M mutable, which means that there exist deformation family over the M in MF. So now not just one parameter, but all of those one parameter deformations can be combined as long as M is as long as F is immutable. And again, there is no restrictions on it, like any Laurent polynomial. Such that the Cordero-Spencer map is injected, so that it's not like some kind of a trivial deformation. It actually deforms. And then additionally, if F is maximally mutable, I will define it what it is, maximally mutable, then we cannot extend it over a larger smooth base space. So if you take maximally mutable, it means I cannot just add another variable and extend it over. So there is no larger base space that you can build a deformation over it. So in some sense, it is maximal, though this is not still a statement that this is a component. So there is something needs to, I mean, basically what needs to be still proven that, or what I don't know how to do is how to treat what if the, so the base space might be singular. It's not known whether it's singular or it's smooth. So if it's smooth, then I can say what the components are, but yeah, you have to show that it's actually smooth. So I can only make the following conjecture, which is basically upgrade of the conjecture that we have with Alessia and Andrea. And so the upgrade is that so basically this theorem stated in saying that this is actually a component, so meaning that there is one-to-one with deformation components of xp. Now all deformation components are one-to-one with maximally mutable maximally mutable Laurent polynomials f with Newton polytope equal to b. And additionally, only smoothing components come from the previous conjecture. So smoothing is if it's zero mutable, if it's maximally mutable, then you just have a deformation component and it's not a smooth. So this is just based on this result. And so you can extend this last statement somehow suggests that if everything is smooth, then probably this is the deformation component.
And so now this really depends on F itself, not on delta.
Yes.
As in the proposition,
Yeah.
the family.
But this is one parameter and this is multiple.
If you have one parameter, then you don't need to actually know F, but to combine several parameters, you need
That's
to use F,
yeah.
and you have different F and they combine.
That's the motivation explained. So F tells you which of those one parameter deformations you can take to find.
And do you know if do you know something about the general fiber of these components?
Yes. I will talk about it. So far I'm just saying that the general fiber is smooth if it's zero mutable. And that's it, but I will so I have 10 minutes. Yeah, you're the chair. If you're interested, yeah.
And I can give you 10 minutes.
Sure. No, I will try to. Okay, so just to okay, just to finish, let me just start. I mean, basically stated the main two the main two. So how to prove this theorem by two theorems? So by two smaller theorems. So the first is the first we need to prove that is unobstructed in in MF, if and only if the mutations is unobstructed. So mutation mg is unobstructed in M, and then you have mutation mg. So this is the so that you connect basically that unobstructedness is the same. So if you mutate, it stays unobstructed. And so the main somehow idea is to show that whenever you have a deformation family, when you build this one parameter deformation, that you can actually mutate Laurent. So like if you mutate this guy that has 2 inside, we mutate it to here. And then basically the statement is if this guy is 2, 0, minus 2 mutable, then this guy is still 2, 0, minus 2 mutable. So basically what we need to prove is that we have kind of on mutations, we can mutate with some nice properties, but then also on algebraic side. So the deformations, actual deformation family can also be mutated in the same way. So this statement actually holds. And to do these mutations, it's quite hard. So to do to actually show that the deformation family can be mutated. But that's the main idea. And in fact, this statement, whenever you just use mg, it can be stated also for any dimensions. And this statement actually holds for any dimension. But then, okay, not proven yet. Yeah, but I mean, so the proof is again just for 3 dimensions. But this statement should hold in any dimension. But then there is a theorem 2 that really strictly depends on 3 dimensions, and this is that f can be mutated. So this is 3 dimensions. Can be mutated to G such that there exists V inside the Newton polytope such that so M of V is less than 0 for every M in Mg. So basically you have kind of fixed point with all mutations of G. So and this is like convex geometry statement that holds only in 3-dimensional. And corollary of this statement is basically that. So now I will. So if you are familiar with this rigid context, now let me give just a definition. I still didn't state what maximally immutable is, so it's a very natural definition. So F is maximally immutable if it doesn't exist G with Mg strictly bigger than MF. So the set of notation is maximal. Okay, here of course G with and Newton polytope. So this means maximally immutable. It's a natural definition. And then corollary of theorem 2 is that 0 mutable is the same as rigid. Rigid, okay, so rigid means in this sense, so what I'd like to call this, definition that F is rigid if there exists G with if there exists G with that is M mutable for M. So for all the mutations of F, then F equals to G. So rigid means that all the coefficients are already determined by mutation. So and then another corollary is that rigid is maximally mutable. And so 10 years ago, Kasperczyk and Coates called Laurent polynomials rigid maximally mutable, but maybe with those in those settings, I think it's better to just call it rigid in this sense, and then show that basically rigid is maximally mutable. Yeah. Okay. So
only in dimension 3.
yeah, corollary works only in dimension 3, but so like my time is almost up, so I can just say what I expect in higher dimensions. So this guy, so I mean, so why is this theorem important? Is because then affine toric variety corresponding to this delta G, I know it's an obstructed by cohomological theory. And then I can then I can use theorem 1 to even show that the first one is an obstructed. In higher dimensions, the obstruction space is much harder to understand. So and that's why I don't know whether it's possible to mutate it. So if we manage to mutate in higher dimensions somewhere that we know it's an obstructed, then basically the first conjecture is proven. But this probably maybe it's not even possible. But what I believe is possible is this affine version of that if we take rigid F, any dimension, then we should be able to mutate it to something that to G that Newton polytope is terminal. And for terminal ones, this is upcoming result. It's unobstructed. So the terminal affine Gorenstein toric varieties are unobstructed. This is not published yet, but it will be soon. And then you know that by theorem 1, the whole thing should be unobstructed. If you want projective setting, you just deal with mutations that have not affine function, but you have like a point that is 0, and then it has to be linear function. And here it's actually interesting thing, because I think in the affine setting, if you take rigid ones, I believe you can mutate it to terminal. So terminal for me means that lattice points are so the vertices are like the only lattice points of the polytope. This is maybe not a conventional definition, but I just call it terminal because it corresponds to terminal function. So if you have this linear function, it is always 0. Then I guess theorem 2 should be harder to prove, because you don't know to where to mutate it in the projective sense, that it's an obstructed. So this is the main difficulty, how to come from projective to affine. But otherwise, you just like whenever you consider these projective mutations, that it's you have a in projective setting, you always have a 0, and so then the whole theory works the same. It's just that this theorem 2 is. That's all I want to say. Thank you.